All right, I guess we're at time. So people will continue to wander in or not. So welcome to the UFM research group at IETF 121. So my name is Stephen Farrell. My co-chair Jonathan is on you're not on a giant screen, Jonathan, so you don't have to worry about a 9-foot head. So Jonathan is remote this time because he has a busy week ahead next week. So we should congratulate Jonathan on his upcoming nuptials. So that's all right. Best of luck with that. So for today, this is the Note Well, which you've probably seen before. I think there is a version of this that's tailored for IRTF research groups that I failed to find. So this doesn't reference the IRTF, but you know where you are. Meeting tips, I think you probably have seen these. If you're remote, please pay attention, etc. We don't have a huge crowd, so we can be a little bit lax with the queuing discipline if need be. But if you're here, please join the room in the data tracker. And if you would join the queue, that would be nice, but we don't necessarily have to because there's not that many of us. Here's our agenda. I didn't update this slide. We have a slide update to the agenda. So we have a brief announcement. I guess, Joe, you're doing it, or is Rich gone? Rich is gone. Joe did it. Just a brief public service announcement, I guess, from the TLS working group. Kind of. So Joe's going to do that in 5 or 10 minutes at the beginning, and then he has to run off. And then we have tested TLS and iMessage. And time may well permit this time that Jonathan has had this delegated credentials presentation that's been at the last item on, I think, every agenda we've had for the last couple of years, and we've never gotten to it. We have a good chance today. And then any other business. So any agenda bashing? I don't see any agenda bashing, so let's go ahead. So Joe Salloway is one of the co-chairs of the TLS working group and wants to tell us a little bit about something they're doing there.
Yeah, so many of you may already know that we have been working on putting a process in place where we can kind of have formal review of the protocols, cryptographic review, etc. And we're getting pretty far along where we feel like we've starting to get it to a place where we have a process defined, where we have a panel of experts, and that we can ask for them to review and provide an assessment of things as we adopt them, as to whether they need review, if they're going to change the properties of TLS or add anything new. And then at various points throughout the process. And so there's still more work to be done in terms of making this a smooth and efficient process, but we're getting it off the ground now. I thought we'd come here, and many of you, I think, already know this, but it's if you want to hear more, I would come to the TLS meeting on Friday afternoon.
So again, I mean, I guess just in case somebody doesn't know what TLS is.
So TLS is Transport Layer Security. It's one of the most widely used security protocols on the internet. And you probably have heard of it.
Yeah, I guess, but it's also one of the protocols that has had the most formal analysis, I guess, right?
Yeah, I mean, and some of the people here have been involved in reviewing and doing analysis on TLS 1.3 and various extensions to it. And so that's been really a good experience for us. We'd like to continue and keep that high level of assurance going with the new things that we're adding.
Jonathan.
Yep.
So unfortunately, I wasn't able to make the FAT interim. Was it formal analysis task force? Task something?
Maybe it's triage team. I have to ask Deirdre exactly what the acronym translates to, but something along the formal analysis triage team, let's say, for right now.
Okay. Yeah. And one of the things that I remember coming up at the last TLS meeting was that there's no mechanism. Once the triage team have said, yes, this breaks the previous analysis, there's no mechanism to commission or arrange another analysis. Was that addressed at all?
That is still kind of a rough point in the process, in that there is, we're relying on, community involvement to try to get the reviews done. And so that is something maybe with this group, we can try to help get to the point where that's an easier process for people. Ideally in the fullness of time, like this would be something that we would have people who are participating in the working group who would be readily, easily available to do. But we're not there yet, right? So,
So I guess I think maybe two suggestions. One is as the kind of FAT process firms up, and it's kind of experimental, but as it evolves, it might be nice to just drop a mail to the UFM list, kind of with where things are at.
sure.
And maybe also if as that team kind of produces analyses, if somebody doesn't have to be the chair of the TLS, but if somebody basically would forward on mails that are related to the formal methods thing, especially if there are issues with usability, I think that would be, if somebody says I have this draft, and somebody comes back and says, which I think has happened already, analyzing that would be so much work because, and therefore it's not worth it. Then I think that would be a useful piece of information to send to the UFM group.
So kind of feedback on what the outcomes are, or like what would be the most useful sort of.
So I think just like a pointer to outcomes, but I think the most useful thing might be, here's why it would be too much work to do an analysis of this draft, and then hopefully in the fullness of time, the UFM research group would be studying that usability problem. That's what the U is for, right? Because I think that happened already. That somebody's
yeah. Jonathan could probably speak a little bit more to that, but yeah.
So if I remember correctly, Rich had a draft that in general looks pretty safe, except changes something that we assume at the very, very bottom of the little tree of proofs we built. And so it's more like we'd have to redo the analysis from scratch because it breaks a fundamental assumption. And I think we could definitely learn from that, maybe we could restructure our proofs or something. But I think the real thing to take away from that is a full analysis from scratch shouldn't be so painful. That would be.
And another thing there is maybe we also that's Russ's draft, and we came to this late. It's already a published draft, and we're looking at elevating it in the standard from a proposed to a standard, right? And so we wanted to do the review at that time, and maybe there was something that could be done at the time when it was being designed that would have made the review easier as well. So I think it can go both sides there.
Great.
Right. Thanks.
Thanks, Joe. I think it's good that that's happening. And jump up. Mohammed.
I have a quick follow-up on this. So one thing that I would like to be addressed is what is the incentive for someone who wants to do the analysis? Like a couple of people approached me, hey, I have a draft. How long will it take this draft to be verified? Like we have to do extra work in order to analyze that or to see what is in that draft and try to estimate that. I would like this thing to be offloaded to that triage team. I think that can probably give some more guidance that, okay, so we think this is I think it was in the initial proposal. I'm not sure if it's still there. It was that this is the kind of estimated effort that we think is required for this draft, and these are the expected properties to be analyzed for this. So because if people approach us, we are more than happy to analyze it, but what are the incentives for us to do that? So we are also researchers. We have to we have to think about how it relates to our research for which we are funded, right? So that's one thing that I would like to be considered in the proposal, at least from our perspective, from the UFMRG perspective, if someone is interested. And secondly, how much the triage panel will be involved in helping out if we are kind of stuck at some point in time, or we need more clarification. I think there is a license, but it was not clear to me how does it happen, that what will be the kind of latency is involved, like if I contact the license, for instance, if I'm doing the analysis, what will be the kind of latencies involved, like if we contact the license and then it contacts the person and then how it comes back to us. So there were some questions around that in the presentation. Unfortunately, I couldn't also make the interim. The time selected was not suitable for me. But I would like
Sure.
some clarifications on this in the process.
So Jonathan's in the queue. Or Joe, do you want to have your clarification? I mean, by the way, I would just say that I wouldn't worry about liaisons. This is not a these people are not millions of miles away from us, so we can just talk to them.
I think this is, if you can make the TLS meeting on Friday, then we should have that discussion there, because it's kind of about the process and how there's a liaison between the working group and the BAT group, right? And that, yeah, Stephen doesn't like that part, but so those types of things we really need some feedback on, and it's something that we need to work through, right? I don't think we don't have it completely right yet. It'll take some time, but the more kind of feedback and collaboration we have from people who are doing a lot of this work will be helpful.
Jonathan?
So to directly answer your first question, at the moment, because I think, especially with Russ's draft, I think the result is going to be, it's all fine. It's going to be quite difficult to try and publish that as a result, because it's not novel. The thing that looks probably fine when we did a bunch of work is actually really fine. It's like not hugely engaging. But I think Colin's in the audience, and he did suggest that we might be able to use whatever pathway the ANRW uses to publish papers in a sort of UFMRG journal. I don't know what it would be, issue of some, I don't know, something. And so maybe that would be the way we'd be able to deal with this. Like you'd get a publication and we would actively be happy to accept, yes, this is secure results, or, as well as, no, this is broken results.
Great. Okay. Thanks, Joe. And again, if you're interested in the topic, please do go to the TLS session where we'll be discussing this. Colin.
Hello. I will figure out how to join the queue.
That's okay. We're a small group and friendly.
So yeah, I mean, just on that point, I mean, the IETF does have its own academic workshop, which publishes its results in its papers in the ACM Digital Library, and we have a control of the process by which we select the papers there. And the ANRW has traditionally worked as a fairly normal academic workshop and done the peer review in the fairly normal way. But if we choose to decide that we want to run special sessions on particular topics and review the papers in a way that perhaps focuses on usefulness and correctness rather than novelty, I think we can choose to do that. So, if this is a useful thing to do, I would encourage you to work with the program chairs for NRW and to think about whether it makes sense to have a special session to publish formal methods results, for example.
Yeah.
And the people who are proposing the sustainability group are also talking about running a special session on sustainability. So we have flexibility to do interesting things there.
Cool. And the time frame for that would be July. It tends to, NRW happens at the summer IETF.
The NRW happens in July, so you would want to be talking to the program chairs over the next couple of months.
Yeah, and then in terms of, I guess, collecting existing analyses, especially the ones that say didn't find anything, which can't be published elsewhere. If people had stuff ready in the spring-ish, that would be timely for that.
Regular paper deadline is usually April-ish, give or take.
Yeah.
So
yeah. Okay. Okay, I've made a note that myself and Jonathan should come back to this. Great. Thanks all. And again, if you're interested in the TLS thing, go to the TLS session. So next up, we have Mohammed. So you can just, I don't believe this is going to work because I didn't do it into my computer to break it. So you just tell me what to go to the next slide.
Okay, so it would be easier if, also because I have a lot of transitions?
Yeah, but you don't have
Okay,
to just tell
okay.
me.
Okay, sure.
I take instructions well.
Okay, sure. I hope you don't hurt your finger. So there are a lot of transitions anyway. Okay. So welcome everyone. So this is joint work with Thomas Fossati, Hannes Finish, and Simon Frost and Ned Smith. So the usability perspective here is that how do we actually write the specifications? I believe that if we can help people writing these specifications clearly in a way which are accessible to these people who write these specifications, then it's already a lot of help. That is then also help for formal methods that we can actually then verify them. So the way it started was like 2 years ago, Hannes had a proposal that he wants it to be verified, the tested TLS draft, which is the next slide, please. Next one. So this work, Hannes had this draft, which is for Sati TLS attestation, and he proposed or asked for volunteers to verify this, the security of this draft, which is combining kind of attestation in TLS protocol. And I volunteered for that. It was, so we are still, it's a work in progress. So this is one part of that. The one I presented in the last IETF was the pre-handshake. I will come to these points. But this is the relevance to the IETF. So this is directly supporting that draft. Next, please.
So just as a question, would you prefer questions at the end or people?
No, it's fine. So
Okay,
you can
so-
just queue up. So whenever you have questions, feel free
Great.
to. So it's more of a discussion. I do have specific discussion points as well, where I would like some feedback or your input. And if you have any comments or questions, feel free to just jump up to the queue. And so as a background, I will first just recall what the TLS protocol is. You just heard from Joe. It's a most commonly used protocol in the internet. And the way it works is the security is that the client and the server have a private key. That's the TLS identity key here written as a priv tick -c for client -s for the server. And they both depend on the security argument depends that there is some certification authority which issued this a certificate that this is the genuine thing or an authentic thing. But what if that key leaks out or is compromised? There is no guarantee at all. So the all of the security argument is based on the protection of that specific key. And if by any means, and there are several means that I will come to, that there is the hardware, there is software, and a lot of stack in between that can actually leak out that key if there are vulnerabilities in that. And that's what that's where the whole security argument of that fails, that even if I have that key, it's no proof that somebody else also has that key, which is that it's compromised or leaked. So next slide, please. So these are the two parts of TLS. And what we have to do that is the endpoint security, which is remote attestation. There is RATS working group, which is working on defining these kind of things. RFC 9334 defines the RATS architecture, which is something like this. We have the verifying relying party, and on the other side, we have the attester. From RATS architecture, I have simplified the picture. I have combined together verifier plus relying party, as I also had in the last IETF. So just to simplify the figure, my argument here is that if I have concerns in simplistic view of combining these two these two entities or roles, I will definitely have issues also in having these two separate, which means that the RATS architecture never defines what's the connection between, and even the TLS draft, which we are considering like for Sati TLS attestation, it never defines what is the connection or what is the security between the verifier and the relying party. It only talks about the two things. So that needs to be considered. So we simplified the picture, and the argument is, as I mentioned, that every issue that applies here also applies to that specific case. And there are additional issues which we will consider when we have this separated out. So the way it happens is there is a nonce coming from the verifying relying party. It generates there is target environment and a testing environment. The target environment is the one which is being checked, and a testing environment is some trusted entity within the attester, which is collecting these claims, signing these claims, typically done by signatures, and then sending over this evidence back to the verifying relying party. And appraisal is just a fancy word for verification that they use, that it's going to verify that evidence along some reference values and other things. Think of this as the verifying relying party having the hash computed on a secure machine, let's say my own laptop that I trust, and the attester is now in the cloud. I want that the hash that I computed on my specific machine to be the same which is coming from the cloud. So these are the claims, the hash of the code I got, and that should match the one that I computed on my secure machine, my own laptop, so that I can trust the code running on the cloud. So that's the kind of the use case which is confidential computing. Next slide, please. Okay, so we have now seen the TLS and the remote attestation protocols, and the attested TLS is simply the composition of the two protocols. That I have TLS, I have remote attestation. One way to do attestation is that I establish the whole security, the secure channel, do all of what the TLS is doing, and then do this protocol which is shown on the left, that I send over nonce over that secure channel and do all these things. That's an overkill, because all we are doing is we are repeating the whole TLS essentially, right? So what we can do better is actually combine them or compose them efficiently within the TLS protocol, such that it's proven to be secure via found methods, which we will do. It's a work in progress, but we can still be sure that we are not repeating that what is already done in the TLS, right? So I mean, rather than creating a new protocol which is essentially creating a secure channel and doing all that attestation again, we compose it efficiently within the TLS that exists and the libraries that exist. We extend those libraries so that we can actually do attestation also. So there are 3 different ways of composition. Next slide, please. Which I will talk about in the specifications. And now this is how we visualize it as a triangle, like pre-handshake attestation, post-handshake, and intra-handshake. Next, please. So essentially what I have is I have 2 things, remote attestation and TLS handshake. I can do first thing first, and then the second one, or I can do it the other way around, or I could merge them together. These are the 3 fundamental ways in which we can combine them together. So pre-intra post is exactly showing that. And the input that goes from remote attestation to the TLS handshake on the left side, pre-handshake attestation, is the attestation credential. RFC 9334 defines evidence and attestation results. So they can be, AC represents any of those depending on the configuration. So TLS exporter, the middle picture, the post handshake, we have defined, so there are defined, sorry, the last one again, please. Okay, so we have exporters defined for the TLS section 7.5, where we can export some key material into some other protocols. That's exactly what this is doing. The post handshake uses these exporting key materials for that into the remote attestation part. And finally, the proposal actually is the draft for SATI TLS attestation is actually the intra one, where it's saying that the TLS and remote attestation are efficiently combined together, and we have a strong binding such that both happen together. That is, we use the TLS exporters to put into the remote attestation and then export back the evidence into the TLS itself to carry it on, so that we don't have to do one after the other, rather compose them efficiently together. Next, please.
You have a question?
Yes, please. Sure.
Can I briefly? So maybe this is just me reading too much into your diagram.
Mm-hmm.
But there's also the possibility of interleaving, right? So you send the first message of the remote attestation, do a full TLS handshake, send the second message of remote attestation. Like, it's not just combining them, you can also interleave them. It's a fourth option here.
I think by what I mean by intra is actually interleaving. So this is actually combining. So exporter is used in remote attestation, and its remote attestation still happened before the TLS handshake finishes. So this is the certificate message which is carrying the remote attestation. So they are interleaved together. Sorry if I was unclear. So this is exactly the interleaving of the two. Probably I should make TLS a bit more bigger to be clear that it's still happening within the TLS. That is the smaller one. I wanted it to be really in the part of that.
What I mean is more if you think of TLS, it's 1.5 round trips, assuming we're talking TLS 1.3.
Yeah.
And remote attestation is 1 round trip.
Mm-hmm.
So are we talking sending 5 messages, or are we talking sending 3 messages?
No, it's only the same messages that TLS 1.3 handshake has. So using exporters and evidence is a part of the certificate message. So There are two different designs, but the design I am going to talk about is only that certificate message carries that evidence. So there is no new message or any new round trip involved in the intra handshake proposal. Post does have extra round trips, but in intra, we want to be keeping it the same as the standard TLS, only
Okay.
extending the messages.
Mhm. Okay. Okay.
Right, thank you. So next one, please. So the protocol specifications, how do we write from TLS perspective? This is now 2 layers of simple model. We said we talk about 2 entities rather than 3 in the remote attestation. We had attester and verifying relying party. In TLS, we have 2 roles, server and the client. So there are 4 possible, actually 2 combinations for both of them, saying that server is the attester, which means that the client will be the verifying relying party, right? And the next one, please. That is the client as the attester, which means that the server is now the verifying relying party. If we have these roles, verifying relying party. Next, please. So I will then first talk about the server as an attester, and this will clarify what we actually mean by that. So generic protocol here means that I am covering all possible cases that I showed. That is pre-handshake, intra-handshake, post-handshake. And message 2.1 that you see, the certificate message that is extended with the evidence. So no changes within the TLS handshake. It's just using the extensions of certificate message to carry the evidence along. And it's the same for both pre and intra, because in pre it was generated right at the top before the TLS handshake even begin, right? And in intra, it will be generated after it received the server hello message. It will generate that containing that nonce, the client hello. From the client, when it received that nonce, in addition to the TLS nonce, there will be attestation nonce, which will be added to this. So client hello message will be extended with the TLS attestation nonce, and that will be then signed in the step after 1.1. And then that evidence will be transmitted as part of 2.1. And finally, we will have when the client will receive it, it will be then doing the appraisal of that form, of that evidence. So in step, let's say, before 2.4, it will do the appraisal, check the appraisal, and then send over the finished message. For post handshake, if we come to the point 3, that's the real bottom of this. So post handshake was TLS handshake has now finished. And then we have this handshake happening. This is where I think Jonathan was asking. So this is only in the post handshake. Now I need to send over a nonce and then generate the evidence, because it said there is no change in the TLS handshake. It has now finished. And over that secure channel, we send over the nonce and then create an evidence. So this needs an extra round trip for that, and is only applicable to post handshake attestation. And right, so next one, please. So this is the other possibility, which was the client as an attester, which will mean essentially the server as the verifying relying party, which is shows on the top as the legend TLS roles, RA roles. And then basically what changes here is that essentially I can transmit as, so the certificate needs to request a certificate, because it's an optional thing. The client is not by default authenticated. So client server will request a certificate via message 2.1 as in the standard TLS. Nothing changed. The only thing that changes is in the blue, in the green, which is that the certificate will now be the certificate message from the client 2.5 will be extended with that evidence, because client is the attester, and it's in both pre or intra. And as before, the post will be that the handshake has completed as the standard TLS was, and at the end, the verifying relying party will send over a nonce, attester will generate that evidence, and then send over as a separate message over that secure channel. So steps shown in step 3. Next, please. So now we have 3 different options. Just at a very high level, I want to go back to the high level picture of how this will work, which is still taking the client as an attester and showing all 3 options, because by generic, I mean it was for pre, intra, and post. And now I will show the whole 3 things separately. Pre-handshake attestation means attestation evidence is generated before the handshake. That's shown on the top left. Client generates an evidence. Then the TLS happens and it has to convey that evidence. So the conveyance part happens as part of the certificate message. And at the other end, when before the TLS finishes, it does the server does the appraisal. It checks that everything is correct, the hash of the measurement is correct, public key and all that, everything is correct. Then there is a secure channel. Next, please. Second option, intra, where the internet draft is. So what it says is that the generation of evidence will happen within the TLS handshake, and that's where it's shown, and it will still be conveyed as part of the certificate message. And at the end of that, so at server side, there will be the appraisal of evidence. The only thing that changes is generation happens within the evidence, within the TLS handshake. Next, please. The final option, which is that the post-handshake attestation secure channel as in the standard TLS. Afterwards, attester generates evidence. Here, client is the attester, conveys the evidence over a separate message. And what's not shown here is the nonce coming from the server to the client. And then there will be conveyance of evidence, and then finally the appraisal of evidence at the server side. Next, please. So this is the design space that we have fully explored. Like when the internet draft was there, as researchers, we don't only go for the internet draft. So we explored fully that what are the existing options. Do we even need this internet draft? That was one of my initial questions. What is your motivation of writing this whole internet draft? Why do I need to change the internet? Why do I need to change the TLS handshake? Was my really first question. And that's what I wanted to explore, that is there any option that I could do? And then we came up with this concept of pre and post like thing. And then we saw that actually there are implementations that exist and people actually use it. And in the pre handshake, for instance, there are 3 different design options that people use. That is the certificate that is used, is it self-issued or whether it is issued by the TA, that is the trusted authority, or whether it's issued by the certification authority. So these are the 3 options on the left in green. And below that, there are different implementations which are written. That is Intel's RATLS uses self-signed certificates. Verizon is one implementation of the TS issued credential. And attested CSR is another draft in the LAMPS working group that's using the CA issued certificates. So the intra has 2 options. They are both internet drafts. The TLS attest is the draft which we are working on. And there was previously a draft which didn't use negotiation. Negotiation is important because like there are many trusted execution environment. Intel has its own solution. Intel and ARM has its own format of the evidence. AMD, IBM, and so on, we wanted to standardize that. And the way it happens is that they negotiate, hey, what is the format that you want, that you support? And then the other party agrees to that format of the evidence. So we don't no longer have to care about Intel, ARM, AMD, and blah, blah, blah. So we agree, add that negotiation as part of the server hello and client hello. And that's where the negotiation part is. So without negotiation, that was the older internet draft. The one we are talking about is the with negotiation. And finally, for the post-handshake attestation, one of the benefits of doing this exercise, exploring the whole white space, was that RFC 9261 can actually be used as a useful solution to design this space that was never explored. And Hannes, Thomas, and I are working on writing a draft on this, which is that will explain exactly this thing, that how we can add attestation into using RFC 9261, which has not been explored, and how this will work. Anyway, the other 2 are standard RFC 8446 things. So section 7.5 defines exporters. One can use these exporters to do this. SCOAN is one specific implementation for that. And then we have sections 4.2.6 and 462 defining the post-handshake exchange over which we can also transport that evidence. So these are 3 different ways within or 3 different design options within pre, intra, and post. And the question I would like to discuss to the research group is that, is there any fundamental design option that you see missing here? Or does someone has any opinion on something that could also be one of the design options and not yet explored? If someone has any insights.
So, yeah, hi. So I have like a lot to say about all of these, so I'm going to try and not take your entire time. Exported authenticators is a really interesting solution. But the properties you get from it, I did the analysis of exportable authenticators. The properties you get for it are very subtle and not necessarily exactly what you're looking for.
Okay.
Notably, if you send two exported authenticators on the same connection, they don't authenticate each other. If I recall correctly about post-handshake exchange, we were never able to prove that it had the same guarantees as TLS 1.3 normally. And I don't think the ProVerif folks were able to either. So basically, there be dragons. Actually, you've got this on later slides, so I'm going to stop there and pass over to Felix.
Sure. Thanks.
Felix?
Yeah, hi, I'm Felix Linker, ETH, Zurich. I find it hard to comment on your question. I mean, this might be because I am not an expert of remote attestation and the likes. However, the critical thing I'm missing are the requirements. Like, you started drawing a design space here, but I don't know what the security requirements are that you're looking for.
They're in the next slide. So
and I would say, you know, like, if we have this big, I ignore all the industry consensus. Like you said, we want to solidify the space between ARM, Intel, whatever, right? These will be complicated discussions. I could see why you would go for one or the other because of like legacy arguments and all that kind of stuff. Yeah, but if we just look at the security requirements, I think you can just pick whatever you want, and if you can prove that you fulfill the security requirements, then you're good. No? So
I don't think this works this way. So this is not that easy. So this is a very simplistic picture of that. But anyway, they have the pre, intra, and post have their own security properties. And that's what we analyzed. And within that, the design options that I show, each one of those has different security properties. Of course, we have not done the formal analysis for each of those. We have only done for Intel's RATLS. But in short, what I would say is they have different security properties. We cannot just randomly pick up any one of those and just build a solution on top of that. They have different security requirements. Intel's RATLS, for instance, does not provide you the freshness because the evidence is pre-generated.
Yeah, my point is, I think before you start cutting down or like exploring a design space, you should explore the security requirements.
Yeah, they're there in the next
slides. Independent of the design. I know that in practical development, one informs the other, because sometimes you see, oh, but we have this hammer, so maybe we can like also add this requirement. We previously didn't do it because we thought it was impossible. But now we actually can. So maybe I think we need to comment on this meaningfully. I would need to see the security requirements.
Yeah, sure. So I have a comment there as well. So RFC 9334 is super vague about this. We don't have any security considerations written down properly. TLS, of course, has very nice properties, but it's in one of my slides. Yes, please.
Joe Salloway, one question with the pre-handshake in the CA issued case. Is it that the attestation happens as part of the process of getting the certificate, or is it a separate? Okay.
Yeah. So the way it happens is that the attester first contacts the certification authority, provides its evidence to that certification authority, gets back an attestation result, kind of a passport. Now I have a passport, I can use it for certain number of years that I can show to everyone, hey, I am this. So this is kind of authenticating me for for a duration of the period.
Right. Okay, thank you.
Yeah. Cool.
So I had a question as well.
Sure.
So this is kind of related to Jonathan's comment question. So that if I count right, there's 13 leaves on the tree here. So just 13 different ways of doing something.
They're not the okay. So let me.
They're doing slightly different things. Sure.
Yeah, sure.
So my question though is, if you were to analyze these from the point of view of how hard it is to prove some results, is that a way of pruning the tree before you actually do all the work, or do you have to first do 13 formal analyses, which is impossible, and then go back and figure out which one were easier or not? Is there any way ahead of time to know which ones would be easier to prove? But based on your own experience, you might be able to say, but from just looking at this, is there a way to decide which ones to explore on the basis of which are easier or harder formally?
I think that the pre and post are easier to analyze because they are kind of using the standard TLS, injecting something in or out of that, going back to the figure which was showing the inputs and outputs. But intra is definitely much more intrusive. Changes to the TLS stack needs more effort. That's definitely something I can say at the top level. But up to after the second level, that's not exhaustive. I mean, Intel's RATLS is not the only option in self-issued. There are various others. This was just to explore the design space, what exists, and why we should actually go for intra. I was in the beginning, I was not very supportive of using intra. Over the time, I have become convinced that it's a strong binding. But yeah, the way we started was Intel's RATLS, which is the motivation for doing that was 90% of the confidential computing solutions actually use that specific protocol. So we analyzed that, but of course, we will not analyze everything which exists there. The ones which are really interesting or require have some motivation, which are used in the industry, will be the ones that we will verify.
So Jonathan, Steve, is it just something in the physical mic line before you?
Yes,
Thank you. Steve Crocker. So I liked the question. I liked even more the response. And I was thinking about something similar, so I want to go on that. So with a tree like that, the question is, so how do you evaluate which of those options is preferable? And you chose how hard it is to prove. Frankly, from my point of view, that's a one-time problem. And there's other metrics that one could apply as to how well they work and how effective they are and what the cost of operations are and so forth. But the general question of can you apply some metrics across these in order to evaluate them and be able to compare, I think is a really strong idea and should be included. Otherwise, we just get interesting set of choices here and people will go off and do various things. But making explicit what the metrics are, and there may be multiple metrics and you may have some competition as to which ones you prefer. Thank you.
Sure, thanks. I have a slide which is exactly on that point, some of the trade-offs which they have. Yeah, thanks. Jonathan.
So just very, very quickly, I have this theory that I've written about this before, but I was never able to prove it, that when you're combining protocols and you want compound authentication, which you say on later slides you do, well, if you imagine you're running the protocol 1, then 2 versus 2, then 1, I know you're interleaving them, but they decompose. The first protocol must establish a shared secret, and the second one must have a signature. And given that, if I understand correctly about remote attestation, you don't establish a shared secret, only one way round would seem like it's likely to work. So you might be able to cut either pre or post, basically just by saying we can't get the appropriate compound authentication property.
Okay, so that's Jonathan's law of composition.
Okay.
Yeah, it's like it's my theory, and like it's based on like some work by Kartik.
Let me quickly clarify one thing. So the simplistic picture that I showed assumed that there is a shared secret between the two. So the argument there was that I could replicate the whole of the TLS in order to establish that shared secret. But that's actually only a very simplistic picture that's assuming that there is some shared secret. And the argument was that we don't want to design the whole from scratch, that we do one whole thing for sharing that evidence, and then we do TLS for connection establishment again. Why don't embed or compose them together better? I'm not sure if I clarified that point, but the reason was, so the simplistic picture of remote attestation, I mean, that I showed assumes pre-shared secrets that both parties have, and how they are established is going to replicate the whole of TLS in itself. That becomes pre, right? So that becomes that, it becomes post, that you do TLS in itself, TLS handshake, and then you do the exchange of the evidence. That's kind of still in the post handshake.
So if in the compound authentication case, right,
Mhm.
one of the things you're trying to say is, imagine the TLS protocol was broken, right? Somebody
Mhm.
has like leaked their private keys on Twitter, like
Yeah.
it's broken.
Hmm.
Do I know that that TLS session was honestly run? So it was run by the person I thought it was run by. And conversely, let's say remote attestation was broken. Somebody leaked Intel signing key on Twitter.
Yeah.
Can I now, because I ran the TLS session, can I know that that signature was actually done truly? Like it was done honestly, even though anyone could have made it. I happen to know that it was run honestly. And that's the
exactly. I love that view. And actually, 2 days ago in the hackathon, Cedric exactly mentioned that, and credit goes to him. So we have the channel binding properties that's exactly representing that. That if the whole idea of merging that, going back to the first slide that was in the introduction, was we are composing two things: network security and endpoint security. We should be able to establish that if one is broken, the second should be able to guarantee that, hey, this is broken. If that's not the case, then that's not strong binding. That's why we are pushing towards intra, which is saying that, which should ensure that if one is broken, the other one will say, hey, this is broken, which is not the case for pre and post. So we have these exactly two properties, which we of course have not verified because it was just proposed in the hackathon. But I really want to go towards these kind of properties, and we would love to have your feedback and experience on that. So I think these are very interesting properties, and I do have them in the slides. So we would love to have your feedback on that as well.
Great, thanks. So just as a programming note, Jonathan has kindly offered to not give his presentation again. So we will get to it someday. So Felix, you don't need to worry about time. But if we can finish like in the
It's
next
fine. If we want to wrap it up, I can wrap it up.
No,
It's
no,
not,
let's go for the next like 10 minutes and then to
Okay.
give Felix time. And Jonathan has graciously given up his time. So
Okay, thank you, Jonathan. Right, so we are in the TLS working group in the time permitting slot. So we really are grateful to you for this. So anyway, so the specifications, now we had for TLS two specific parts, which were the key exchange part and the authentication part. The key exchange part is now how we view it. That is how, what exactly should be specified. And that's what we have written in this table, that, and the three columns are representing three different specific implementations. Just as an example, that RATLS is the pre-handshake attestation, TLS attest is the internet draft, and SCONE is the post-handshake. So this is just an implementation guide for, or an example for the specific people who are writing these specifications, that you should definitely write about these things, whether there are any extensions to the client hello and server hello, and if there are, what are those? For instance, TLS attest uses the negotiation that I said about the formats. And then secondly, attestation nonce. So in addition to the TLS nonce, whether it also includes the attestation nonce in these messages. So TLS attest does use that and others don't. And I would love to hear if there would be something else that might be security relevant in key exchange part. I have another slide for authentication part, but this is only about key exchange part.
so just maybe we should press on.
Yeah, sure. So we go ahead. So, okay. So authentication part is, we have now 4 different properties, and for B, we have 3 different parts, which is A is the lifetime of the key. So now there are 2 keys, that is, one is for TLS identity and one that is used to sign the evidence. So how long do they live? So this key is specifically representing the TLS identity key. What is the lifetime of that key? RATLS short term, TLS attest short or long term, and SCONE short term. So this is an example that they should really specify, because there are security concerns related with how long that lives. Then that is the replay and so on, these attacks. And the B part is the certificate message of TLS handshake. What information does it contain related to attestation? And then who is signing that specific certificate? Is it self-signed, or is it signed by the trusted by the certification authority? And then in which format is that specific certificate carried? Like, is it X509, or is it in JOT, or is it in, let's say, CMW? There is another draft which is trying to combine Intel, AMD, ARM, so all these formats into one unified format. So it's negotiated between the 2 participants. And then if there are any extensions in the authentication part, and that means basically like extending certificate messages. And finally, the exporter part, whether it defines any exporters, and if it does, what are the label context and key length. This is important because if we have the same context use as Scone actually uses, the empty context, then all the exporters that we have will be exactly the same during the whole session through which the transcript remains the same. That will be exporting the exactly same value, and that will not be a unique nonce that we can use. Scone actually does exactly that, which is wrong. Okay, so the discussion point here was if there is any other design option, but I will skip that. So feel free to post on the mailing list. And here's the threat model for TLS. We are focusing on a non-PSK handshake. So that is what it works with. And for TLS, we use exactly the same model as Bhargavan et al. So we have exactly that thing. For extended by the remote attestation, we have two keys, as I talked about, one for the TLS identity key and one for the attestation. And we assume in the threat model that the private key for TLS identification key is leaked. If the attestation key leaks, then there are bigger problems. So we assume that that's not leaked. Of course, analysis can be done, but that's a reasonable assumption because there are side channel attacks in these hardware trusted execution environments. There are vulnerabilities within these trusted execution environments that can lead to the key being leaked. That being said, the private AK or the attestation key is by no means, we are not saying that it's not leakable. Of course, there are for SGX a number of attacks which have happened that attestation key itself was leaked, but just as a simplistic starting point, we are assuming it's not leaked. Next, please. So here is the slide on properties. So what we are interested in, base security properties of the two protocols. We have attestation, we have the TLS handshake. TLS has well-defined properties. Next, please. The server authentication, for instance, and so on. Next, please. But on the other hand, the RFC 9334 remote attestation is completely vague about it. They have security consideration section just to satisfy the requirements of the RFC, but that never defines what exactly do we expect from such a protocol to provide to us. So next, please. What we did was we kind of analyzed or thought ourselves what should actually have been provided by such a protocol. And one of the properties is that I want that evidence to be freshly generated. That's the per session evidence freshness, that not only freshly generated, but also linked to that specific session. So there is a binding between the two. Next, please. That the integrity of the evidence is protected. Next, please. And there is something that RFC 9334 never talks about, that is relay attack, and it's really fundamental problem to the remote attestation, that if I am being asked, I am the attester, and I forward that nonce to somebody else to generate the evidence and send, and I then get back that evidence and show is that my own evidence, then I'm faking that person, right? So this is basically, I'm relaying that nonce to provide evidence from a good machine. And if I am compromised, I could show somebody that this is the status of myself, and I could have been compromised, but the other party will think that's good enough. And that's the problem. Channel binding properties, credits to Cedric. He mentioned in the hackathon. Next, please, the two properties that Jonathan was kind of rephrasing, that if connection is established, server and client agree on attestation evidence, binding in one direction. The other one, if the remote attestation appraisal succeeds, the client and server agree on all the connection parameters, that is the TLS transcript. Next, please. Yeah, I will skip. Next, please. So this is the kind of trade-offs that we have analyzed, which is the pre, intra, and post. And it's saying typical because it's only meant to be high level. We have not formally analyzed all that was existing. So it's just intuition from all of the analysis that we have currently done. We have only formally analyzed Intel's RATLS. So the pre-handshake attestation, so we want to add attestation, there has to be some modification. The first row is showing what exactly is modified. The next row is showing whether there is any security concern related to replay protection. And the third and fourth are the performance parameters, that how much delay happens in each of these options to the handshake. And the work in progress is the usability. I think one of you pointed about this, that what's the ease of use of this kind of thing, and the complexity of implementation or formal verification is another property that we want to add to it. Next, please. Okay, so the simple summary, next please, is that if it is underspecified, it's not trustworthy. So we have to specify the things clearly so it can be formally analyzed. Next, please. These are the references that I have used, and I really want to acknowledge Cedric, Jonert, Yaron, and Thore, who have given us very good feedback on this. Thanks a lot. And
I guess we probably skip on to Felix because just in a matter of time. But thanks for that. I think it
Thanks.
throws up some really interesting. Thank you. So, so tell me when.
Cool. Yeah. Hi, everyone. I'm Felix Linker. I work at ETH Zurich, and together with my colleagues Ralf Sasse and David Basin, my supervisor, we analyzed Apple's newly released new iMessage PQ3 protocol. The PQ stands for post-quantum. This talk is about, at a high level, about what you can do with modern formal verification tools like Tamron. iMessage was a very challenging protocol to verify, but I think with the analysis being done, we could actually prove protocols that work similarly now much faster. So next slide, please. Earlier this year, Apple announced that they release iMessage with PQ3, and they called this the new state-of-the-art in quantum secure messaging at scale. And this happened in February. And in this blog post, this is a screenshot from the website. Next, please. They have this neat little graphic where they show 4 levels of post-quantum security. And they claim that they sit at level 3, which is apparently strictly better than level 2, hence 1 number higher. You can see that they say they're a bit better than Signal with PQXDH. Really, what I'm here to do is, what I'm here for is, I would like to tell you why these levels are actually distinct, what makes these protocol different. Let's understand in detail how they are designed. Next, please. So let's look at from a bird's eye perspective at how iMessage works and what its security goals are. So here you see an imaginative conversation between me and Jonathan. Jonathan asks me for my favorite meme. I send it to him, and he has an opinion about it. What would we like for such conversations? I guess you all had them in apps like WhatsApp, Signal. What do we usually want to achieve here? So in general, what we would like as a start is we want secrecy. I want that my meme is only known to Jonathan and to no one else. But we know that sometimes things go bad, and or not we, or someone reveals their session secrets, their signing keys, their ephemeral keys, whatever. In these situations, what we additionally would like to have is 2 other secrecy properties, namely forward secrecy and post-compromise security. Forward secrecy means that if we are in a given point in time and key material gets revealed, we would like past messages to remain secure. So if the adversary learns my meme, they don't know why I sent it to Jonathan. And then we also have post-compromise security, which means under some assumptions, we would like to establish security in the future again, assuming session secrets have been revealed in the past. So the adversary ideally only should see my meme. And then finally, what we would also like to have is some agreement on the messages, some sort of authentication. I want to be certain that I communicate with Jonathan. Jonathan wants to know that he's communicating with me. And then also iMessage aims to provide replay protection. So how does iMessage do that roughly? Next slide, please. Like a very high level view on how the cryptography works that iMessage uses. So at the bottom here, you see I sent my favorite meme, and it should be encrypted. Okay, how does that work? It starts with a layer of symmetric encryption on that message. And what do we encrypt with? We encrypt with a shared key. And I have been using emojis a bit. So the square was supposed to be a magic wand. You have to imagine the magic wand there. Apparently, it doesn't get rendered here properly. And so how do we get this? How do we get this shared key? What iMessage does is it combines 2 mechanisms of cryptography. It combines Diffie-Hellman key exchange style cryptography that has been analyzed very well. It's well understood. We know what its security guarantees roughly are and when they when they can be broken. And then on the other hand, we have a key encapsulation mechanism that will give us post-quantum security guarantees. So let me quickly recap how these two mechanisms in general work. For a Diffie-Hellman key exchange style key exchange mechanisms, you usually have two parties exchanging public keys, and with these public keys, they can establish a common shared secret that comes from some commutativity laws. Not so important, but the important thing is you have a shared secret now established by exchanging two public keys. Key encapsulation mechanisms, they work a bit differently. For them, you have one participant sending their public key to another participant. That participant does an encapsulation. They get a shared secret that they can use themselves. They get a ciphertext that they share with their participant. Their participant can use their secret key to decapsulate the ciphertext, and then they have this shared secret again. So iMessage somehow combines these two. And then what iMessage also does to get agreement is it signs its messages with the long-term key of participants. Next slide, please. So here's a bit more of a detailed view on how that works. On this slide, you see all the key material and how of iMessage and how it is related. On the top half, you see this little HKDF bubble, right? And on top of that, you see the asymmetric crypto that is happening to as an input to go to this HKDF. iMessage uses ECDH, where you combine a private key that is yours with a public key of your peer to get some Diffie-Hellman shared secret. Then we use a KEM, as I just said. A client has a private key. They use that to decapsulate a secret, or they use their peer's public key to encapsulate a secret. From that, they get a shared secret. Sometimes they'll replace this with a 0-byte sequence because we don't want to do post-quantum stuff all the time. And then we also use a root key or a 0-byte sequence if we start a new session. So all these things, we combine these into an HKDF. And from what do we get out of this HKDF? Some entropy that we split into two halves. One half is a root key for the next derivation of the style. And then the other half is used as a chain key, that is the CK here. This chain key will be used to derive a message key, which we then finally use for encryption, and another chain key, which we'll use for the next message. Next slide, please. So iMessage uses the double ratchet construction from Signal to establish forward secrecy and post-compromise security guarantees. This is a depiction that I borrowed from Signal's documentation. You can find it there as well. The idea of the double ratchet is that you repeatedly exchange freshly generated public and private keys. The blue ones here are all ECDH keys to establish a shared secret that you put into your HKDF, and then with some extra stuff, you get shared keys out of that. So iMessage's goal was to make this double ratchet construction post-quantum secure. And the rough idea here is, next slide, please. Yeah, we want to throw in some extra entropy in this HKDF. Okay, we have our Diffie-Hellman shared secret. Let's add something more. So to naively extend this construction, let's now add 0-byte sequences everywhere. And now also, next slide, please. Sometimes let's also do a key encapsulation mechanism with your peer. You send your public key to your peer. They encapsulate a shared secret for you. You get the encapsulation back. And in the next round, you can then wire this new post-quantum secure shared secret into your key derivation. Next, please. So when this happens is determined by a heuristic. In our formal analysis, we don't really care that much about when it's happening. We're just saying it can happen sometimes. It need not happen always. And the novel aspect of iMessage is that it integrates the KEM into the double ratchet. Signal also has post-quantum security guarantees, but they only use the KEM upon key establishment. And by integrating it into the double ratchet, iMessage can provide post-quantum, post-compromise security guarantees. And the remainder of the talk will focus on how we can analyze such a protocol.
Just a question. So in the normal ECDH, there are new key shares every time. In the post-quantum, is it the same public key for the receiver, or
no? The public key will be rolled over as well.
Okay.
Yeah, and it's not. I mean, in spirit, what you said was correct, but you don't really establish a new public-private key also for ECDH every time. This only happens when the conversation changes direction, but yes, repeatedly.
You just rerun with the same. Okay.
Yeah. So Yeah. But yes, you don't reuse the same public key. Otherwise, you wouldn't get post-compromise security. Yeah. Next slide, please. Oh, by the way, feel free to ask questions. My talk should last for 20 minutes. So if anything is unclear, jump to the mic. So what adversary are we considering? Because we must consider now, by doing post-quantum stuff, we want to protect against a specific kind of adversary. Otherwise, we wouldn't do it. So what is this adversary? This adversary is called the harvest now, decrypt later adversary. You probably have heard of it. And on this slide, I'll both cover the intuition of this adversary and also how we understand it. So in general, we think that a harvest now, decrypt later adversary is just our standard active network adversary. Yeah, we allow them to reorder messages. They can drop them. They can insert any message they know. They can do all kinds of things on the wire. Then, as usual in the symbolic model that Tamron, our tool, operates in, we make the perfect cryptography assumption. So we assume that symmetric encryption can only be reversed if you know the respective key. And then, coming to the harvest now, decrypt later idea, we assume that our attacker may obtain a quantum computer in the future. Yeah, they might. And they anticipate developments in quantum computing by storing all the messages now. In our threat model, we say, what does this mean? We say that as soon as our harvest now, decrypt later attacker has a quantum computer, protocol execution stops. And you might think this is a bit weird, why does everyone stop using iMessage as soon as there's a quantum computer? The idea is that the quantum computing capabilities will happen only so far in the future that hopefully we can anticipate them. This means in some sense our adversary becomes passive with respect to quantum computing. As soon as they get a quantum computer, what we will allow them is we will allow them to access all secrets that are derived using non-post-quantum cryptography. But we cannot protect against an active quantum attacker. And this is because iMessage does not use a post-quantum secure signature scheme. So if we had an active quantum attacker, they could just forge the signatures on the messages, inject their own key material, and take over the entire conversation. Next slide, please. So the goals of our research were twofold. We wanted to understand the security goals of iMessage thoroughly and formalize them well. And at the end, I'll show an intuition for how we did that. And then most importantly, we wanted to verify that iMessage actually meets its security goals. And for that, we use the tool of our choice, which is the Tamron prover. So Tamron is also a monkey. I need to say this because I'll make a little joke with it. This is our icon. It's a cute little monkey. Tamron is a protocol verification tool, similar to Proverif. It uses constraint solving in a backward search, and it operates in the symbolic model, which reflects the perfect cryptography assumption I've been talking about earlier. And it has been used in the past to analyze TLS 1.3, the key exchange of 5G, or the EMV protocol, which is used in credit cards. Next slide, please. But I have bad news for everyone here. If we go to the next slide, you'll see them. Unfortunately, related work has shown that unbounded looping protocols like Signal and protocols with mutable recursive data structures are out of scope for symbolic provers without introducing artificial restrictions. Well, next slide, please. This is not quite true. It was believed by some that protocols like iMessage cannot be proven in tools like Tamron, which has motivated new research on other protocol verification tools. But I'm standing here because I want to tell you that this is not the case. We prove iMessage secure with no abstractions asterisk. We will make some abstractions. For example, the perfect cryptography assumption already is an abstraction. But in general, we prove the entire thing. And also in our paper, I will only mention this today because I think it's only interesting to a very niche audience, but I would like to point it out. We tried generalizing from our understanding of how one could prove iMessage. And in our paper, we provide a general proof methodology that also on some smaller examples that we hope can help people prove protocols that loop in a similar way as iMessage does in the future faster. Next slide, please. So, because I don't want to assume that all of you know what Tamron is exactly, I'll make a brief high-level introduction of it. The Tamron prover uses two things to model protocols. On the one hand side, you have multi-set rewriting rules. These define a label transition system. You can abstract it like the picture you see on the bottom left corner there. And these multi-set rewriting rules, they basically model what participants can do in the protocol. They can send messages, they can derive keys, but they also model the environment. You like how for example, a PKI could work. This we would sometimes maybe put into multi-set rewriting rules as well. And then what we add to that is an equational theory. And this equational theory is our abstraction of how cryptography works. And in particular, these equations are important because with these equations, the adversary can learn how to play around with the terms. I have an example here. What you see below are the two equations that define the equational theory for message signing and for symmetric encryption. So in the first line, you see the equation that defines how signature verification is abstracted in Tamron typically. You see an outer function verify, and we say if we verify something that was signed, so you see the sign function, namely a message with a certain secret key. If we verify a signature for the corresponding message with the corresponding public key, then this returns true. The check was successful. Or symmetric decryption, this you see in the second line. If we symmetrically decrypt a symmetric encryption of some message with the corresponding key, so you see the same variable k twice, then we get out of this a message. And from this, with these equations, the adversary gets to play around with everything that is sent on the wire. Next slide, please. So security properties in Tamron are expressed as trace properties using the labels of the label transition system we defined earlier with the multi-set rewriting rules. Security properties are written as what we call lemmas, and what you see here is an example lemma for secrecy. We say for all participants P and messages M, participants and messages, this is not explicit, this is just part of the mental model. We say whenever a message was sent by some participant at time point X, this is not so important here, the X itself, but it is required, then there does not exist another time point Y where the adversary knows M. Yeah, this is a classic way of how you would phrase secrecy. And this K means the adversary knows. Next slide, please. So how does Tamron deal with these trace properties? What it does is it takes this original lemma, you see secrecy in the top line, it negates it. So now it will consider an exists trace. It will consider an exists lemma. And this lemma now says there exists a participant that has sent a message at some time point X, and there exists another time point in which the adversary knows it. What we have here is now a formula that tells us what a counterexample to our original thing was that we're interested in. And what will Tamron now do is it will try to find a complete trace that satisfies this property. And if it fails in this search, which was designed to be exhaustive, this will give us a proof. And if it succeeds, it will give us an attack. And this is, on a much grander scale, what we did to analyze iMessage. Next slide, please. So, don't be scared of this large slide. But what you see here is a high-level view of how we modeled iMessage. And I want to go through it step by step, from left to right. Normally, I would build this up, but I wanted to spare myself a couple of next slide, please. So we start with the setup phase. In the setup phase, we have rules like this little rectangles. They relate to multi-set rewriting rules. We have some rules where participants generate their keys. They do some key queries at some long-term key server, and they can start a session, which gives them a fresh session fact. So this oval is like partial state of our model. We say if a participant starts a session, they have like this what we call session fact, and this is now part of the trace. In this phase, what we do in the setup phase, we put aside all the long-term keys that participants generate and all pre-keys that participants generate. Pre-keys are versions of ephemeral keys that will be generated later that are used to establish a session asynchronously. Now, in the second phase, and you see like this dotted line between setup and protocol execution, this dotted line shows you that there is no formal distinction between these two phases. This is just like a mental model from me for you. In the protocol execution phase, we have two sets of rules related to how people send messages and rules related to how people receive messages. So in the top, you see for sender related rules, they use a session fact and they produce a new session fact and send a message. And similarly, for receiver-related use, they use a session fact and they receive a message and they just produce a new session fact, and thus they go back and forth. And participants can non-deterministically decide whenever they want to switch from sender to receiver role and vice versa. While people run the protocol and with these sender and receiver-related rules, we also, again, memorize all the ephemeral keys that they generate along the way, like elliptic curve Diffie-Hellman keys. Now, the third phase is the post-quantum phase, and this is our model for the harvest now decrypt later attacker. At any point in time, our attacker can transition from the protocol execution phase to the post-quantum phase. If they do that, they cannot go back, and as I said, all protocol execution stops. And what we allow our adversary is, we allow them to access all the key material that the participants have generated while running the protocol, unless it is explicitly known to be post-quantum secure, so unless they are chem keys. Next slide, please. So a quick example of how, like I mentioned the session fact, and this is what our formal model revolves around. And what you see here is all the arguments that go into our session fact, and we require all these arguments to make proofs. And don't be intimidated. There are a lot, and it took some time to figure out all the auxiliary lemmas to prove how they all relate to one another. But you can see we start with some identifier that is used for timing heuristics. Then we have a message counter for replay protection. We memorize the participant's role. We see, okay, who's the participant? And then you see a bunch of key material, right? There's the participant's ECDH secret key, their latest chem secret key. They look at their peer, their peer's identity long-term public key, ECDH, and then a bunch of stuff related to chem keys. And we need to track all these variables because there are a lot of branches and loops going on. Next slide, please. So we can abstract our model as follows. When the protocol runs, this is kind of the view that both participants have. The iMessage will run and people will repeatedly do what is called the public key redshift, where they use new chem shared secrets and new Diffie-Hellman shared secrets that they establish via Diffie-Hellman key exchange and a chem encapsulation to get root keys. So this is the top line that you see here. And in the middle, we have our root key N and the Diffie-Hellman shared secret DHN and the chem shared secret for M. And you see on the left side, I index the chem shared secret with a question mark. I do this because there's non-deterministic branching going on. Like we might have used the same chem shared secret there in the past and the future. It's not so clear. Just wanted to point that out. So from these two shared secrets, we derive chain keys. Then from these chain keys, we derive future chain keys and a message key. And then just for the purpose of my illustration, let's assume now that a participant sends some message encrypted with the message key MK, the one with the arrow here. From this abstract view, I would like to show you now how our secrecy lemma looks like that we proved about iMessage, which you'll see illustrated on the next slide. Thank you. Yeah, very good. So what we established was that messages in iMessage are secret unless one of four things happens. If you look at our actual secrecy lemma, you will see that there are a lot more than 4 branches. So I'm simplifying it a bit, but in essence, this is what we show. 4 things can happen for a message to leak. So first thing, the blue keys can leak. The adversary learns the message key that the message was encrypted under. More or less straightforward. If they know the symmetric encryption key, they learn the message. Then, or what alternatively could happen is the adversary learned one of the chain keys that was derived before the current message key, but after the latest asymmetric crypto. So the green block. One of these chain keys got leaked to the adversary. If that happens, they can either derive the message key themselves straightforwardly, or they apply some more chain key derivations and then later get the message encryption key. Or the third thing that could happen is the adversary learns both the most recently used chem shared secret or the most recently established Diffie-Hellman shared secret. Importantly, they need to know both. There is a way for the adversary to circumvent revealing the chem shared secret directly, because they can also learn a previous root key. Because the chem shared secret is not refreshed every time, they can also bypass learning the chem shared secret directly by getting a previous root key that was derived after the latest chem shared secret got established. And finally, what can happen is the signing key got compromised and the adversary learned that. If they do that, they can just take over the communication on behalf of their victim. So importantly, we say that with this secrecy lemma, we show all of secrecy, forward secrecy, and post-compromise security. And why is that? That is because we allow the adversary to access all key material unless we explicitly forbid them to. And we only forbid them to access the key material that we have colored here. That means if the adversary would learn past secrets that are not colored here, it has no effect on the security of messages that I send now, giving us post-compromise security. Also, if the adversary learned key material that was used in the future or will be used in the future, the adversary has no chance to learn anything about the message I'm sending now, giving us forward secrecy. Next slide, please. And now you might wonder, Felix, you said you wanted to address the harvest not equipped late attacker. Where is the quantum attacker in this slide exactly? The quantum attacker hides in how they can learn these things that I colored, because I say the adversary needs to know the chem shared secret and the Diffie-Hellman shared secret. For a quantum attacker, we give them the Diffie-Hellman shared secret for free. So then the security practically reduces to the chem shared secret, but we show that the adversary needs to know both. Next slide, please. So our proof effort was quite substantial. I have some stats for you here. We proved in total 32 auxiliary lemmas, some of which had significant computational overhead. For example, I didn't time all the lemmas because it takes time to time them, but rather simple lemmas, for example, require 7 hours of computation with 20 gigs of RAM, which includes already proof heuristics that I put in Python. I estimate, and I want to stress that this is really an estimation because it's hard to get exact numbers, but we estimate that this was roughly 2.5 person-months of work. But the good thing is, because we provide a general proof methodology, we believe that this would work much quicker for other protocols that follow similar structures. Next slide, please.
So just the 2.5 months of work for somebody expert in Tamarin already.
Kinda.
And TLS, and the sort of ratchet protocols.
Well, ratchet protocol, I mean, it was me. I would say I learned much more. I have heard of, I guess I know more than the average person about ratcheting protocols, but I wouldn't have called myself an expert in ratcheting here. So in conclusion, while analyzing iMessage, we proved the secrecy, forward secrecy, and post-compromise security of iMessage in one lemma, as I showed you with these colored boxes. We also proved agreement, giving us authentication, and non-injective agreement, giving us replay protection. But the latter two lemmas, they are much simpler because they only rely on the secrecy of the signing keys. So I didn't want to go into much detail here. We used Tamarin to do that, which by some was believed to be impossible. And by giving a proof without great abstractions of iMessage, we show that indeed it is possible. And in our paper, we provide a general proof methodology. I'm also happy to talk about it offline with you. You can find full details in our ePrint paper that is available here. I highlighted the suffix of the ePrint link, but if you Google my name and iMessage and formal analysis, you should also be able to find it. Thank you for your attention. If you have any questions, I happily take them now.
So, questions? Yeah, Gary, please.
You mentioned that for looping protocols, verification is not possible because of some recursive data structures mutually. Is this a theoretical limitation or the limitation of Tamarin?
Well, it is not a limitation. People said it was impossible. by us providing this proof, we show that it is indeed possible. Yeah. There were protocol verification tools that have been developed claiming in their motivation protocols like Signal. I'm simplifying the statement a bit, but protocols like Signal are out of scope for tools like Tamron. And yeah, this is not the case.
Sama, to you, Dresden. So were there any usability perspectives? You said that this protocol was new, right? So there were at least some novel perspectives into it. Did you discover some usability perspectives that you did not have as a developer of Tamron, not seen before? Can you comment on that?
Yeah, it's hard for me to comment on that.
Or maybe let's simplify the question. So because you are a developer of Tamron and you are also doing it, of course, for you is very easy. Let me rephrase my question. If somebody unfamiliar with Tamron was doing the same proof, would that person have some kind of issues with this specific protocol? Is that
it's hard for me to comment upon that. I don't know, right? I hope that it was not that I believe that our work was not trivial. Yeah. I also believe that my prior experience with Tamron has certainly helped me.
Mhm.
I hope that it is now easier for other people to prove similar protocols secure because we provide a general proof methodology. It's mostly in the appendix of our paper because we believe it's for a special audience, right? It's like not for everyone, this proof methodology. But I would be curious for people to take a look at the proof methodology, see whether it makes sense. Tell me. Yeah.
Thanks.
Is there a GitHub or anything where we can download the thing and?
Just go to the paper. It's linked in the paper.
Okay.
You can also github.com/Tamron-PQ3. That's our organization where we have everything.
So I put a link to the paper in the chat for the session.
Yeah, and then in the paper you have a link to the GitHub.
So I have a question. What was the specific claim that something wasn't working? Because TLS, if you think about it, is an infinite loop protocol, right? You can always resume and then tear down and then resume and tear down for as many times as you like. What was the specific thing that they said didn't work?
So I mean, it's hard to, is the King of France bold, right? Because people said it is impossible. We showed it is possible. It's hard for me to comment on what they believed is technically impossible. But I think the tear down and the resumption are independent of each other. No. So my intuition now would be with we have a doubly nested loop of symmetric key derivation and asymmetric key derivation, and they strictly depend on the values you've used previously. And when you ask Tamron to fund unit head trace naively, what it will do is it will just push the secrets that the adversary must know back, and back, right? They can always, you will always get a new case where they said, oh, but maybe the key was a bit older, yeah, and then you need induction and all that to show that this is not the case. And
Induction.
Sorry?
We just used induction and that worked.
Maybe the people claiming that it was impossible should have read your work, and then they could have come up with the same conclusion now much earlier. That could be the case, yeah.
I mean, I don't know how you would do it for double nested loops. That would be horrible. But I guess I'll have to read your paper.
Great. Any other questions or? With that, let's thank Felix. Thank you.
Thank you.
Great. So I think that brings us to any other business part of the agenda now that we've again skipped Jonathan's presentation. That must be about to win the record for the thing that occurs in the proceedings of the IETF most commonly. Any other business? Jonathan, anything from you or? Great. Okay, so we'll take. I think that a note I've taken is to look into the ANRW/publication route and we'll talk about that in the next month or two and get back. So thank you and enjoy the rest of your IETF week. And thanks for the talks. Thanks, Gergely, for taking the notes. And thanks, Jonathan, for taking time out of your, I'm sure, very busy and somewhat tense. Sometimes these are tense schedule. But okay. Thanks. Thanks all. See you next time. Yo. No, it just does it. But in any case, I'm already just going to take a copy myself. Yep. Hey, Steve.
Just wanted to say hello and thank you
How are you?
for the connecting me to Adrian Perry.
Yeah, I mean, I guess everything is slow, but you know yourself. Hopefully it'll pay off in the end.